Chapter 17 sees us back in the C language. We're going to learn some new operators. Remember the operators plus and minus and greater than and less than and so on? We're now going to deal with an entire new class of operators. These have to do with the manipulation of individual bits. I guess before we can go any further we have to understand a little bit about bits. Any integer number, when I say integral number, integer number, I'm talking about ints, longs, shorts and so on, can be thought of as a sequence of bits. I guess we all know that 8 bits make a byte, and so in a long, which is 4 bytes long, you'll find 32 bits. You can think of them all as arrayed. You can almost think of a long as an array of 32 bits. Now you can think of these bits as the representation of the number contained in that integer in binary arithmetic or base 2 arithmetic. If you don't know what binary arithmetic is, then I'm not really going to be telling you in this course. It's not really part of the scope of this course. But suffices to say that human beings tend to work in base 10 arithmetic. There are many other numbering systems besides base 10. You can work in base 8. There's a common one with programmers, which is base 16, which is often called hex. And there's another one called base 2, which is what computers tend to work in, or binary arithmetic. Now, I'm not going to explain binary arithmetic to you, so if you don't know, now might be a good time to go and look it up somewhere. Anyway, I'll give you a little brief example. The number 87, the number that we typically refer to as 87, in other words 87 in decimal or base 10 arithmetic, can be represented in base 2 arithmetic as, now how would you say that? 1,010,111 or 1010111. Now why does it happen to equal that? Well, you look at it as follows. I'd pause the slide here if I were you, if you've never used binary arithmetic before, and study what's going on here. Compare that to what you know about base 10 arithmetic. If you added up 64 plus 16 plus 4 plus 2 plus 1, you'd get 87. So we can think of the integer 87 as a 32-bit number. Remember, it's going to be a 32-bit integer or a 32-bit long. So the 7 bits we've got in front of us here, so that leaves 25 bits that we can't see, so they're all assumed to be zeros. So we'll have 25 zeros followed by 1010111. That makes up the full 32 bits. And that's pretty much all I'm going to say about binary arithmetic. Now, as well as representing a single number in a 32-bit long or a 32-bit integer, it is actually possible to treat that single integer or that single long as a series of Boolean values. Remember, a Boolean is on or off, yes or no, true or false, 1 or 0. Importantly, it's 1 or 0. And in a single integer we have 32 bits. In other words, we have 32 things that can be considered 1 or 0. In other words, we have 32 things that could be considered true or false. So often we use the individual bits of an integer to represent Boolean values. In other words, we can use one integer to represent 32 separate Booleans. Now that's interesting because in the past we've just been using integers to specify a single Boolean, which is kind of wasteful, because a single Boolean will be either 1 or 0, and an actual integer can represent any number, any sequence of 4 billion different combinations, and we're just using 2 of them. So there's quite a bit of wasting going on. And if we wanted to utilize every single bit, we could actually store 32 separate Boolean values in one integer. Now if we do that, we have to somehow have a way of accessing each one of them separately from the others. And that's what this chapter is all about.